for independent subset systems and metroids, we have these greedy algorithms. But for minimization, we don't have anything that is similar to maximization, but we have something called submodularity. Okay, so we let f be a function from a power set of E, which means it maps a subset to a real number, a positive number. Then we say function f is submodular if for any subsets of E, A, and any B, which is subset of E, which means they are elements of power sets, we have this, okay, f of A plus f of B. Now remember, it gives you a positive real number, which is greater than f of A union B plus f of A intercept B. So if this is satisfied, then this function is called submodular. Okay, then we can look at a minimum set cover problem. So given the collection C of subsets of set E, okay, we find a subcollection C prime of C. So this is what we want, with minimum cardinality such that every element of E appears in a subset in C1. So that means that we have a minimum set cover. So let me open up a screen. Or maybe we don't need to. Okay, so maybe I just use this space here. All right, so we have a set E, which has a lot of elements. And then you will have subsets, okay? And so let's say, okay, maybe this is better. So let's say I have these elements, that's E. And then you may have a subset of this. You may have a subset of that, subset of that, and subset of that. So of course they cover E, right? So each element in E it appears in one of these, but I want a smallest. I want a subcollection C prime. So, such that it has the smallest number of subsets in it, numbers in it. So obviously in this particular case, for instance, if I pick this one and pick this one, then it covers E, right? So it has a smallest number. So this is C prime. It's just these two, okay? Original C is 4 of them, right? So that's what we want to find the smallest number. Okay, so now for a subcollection A of C, okay, so it's a which means it's a subset of C. We define that this function f will be the size of all the elements that's so for any subset, okay, for any set, now A is a collection of subsets. So for any element which is a subset, okay, so we take the union of this subset, we take the number of elements of this union, then we call it f of A. Then we can verify, okay, so this is true. F of A plus F of B is greater than or equal to F of A union B plus F A intercept B. So this is submodular. in order to find this minimum, find this C prime, this is a greedy algorithm. So initially A is, or C prime, right? But initially A is empty set, and then while that this f of A does not cover E, which means that it's less than the size of E, we simply choose S in C such that when we add this S to A, this F gives me the maximum value. Okay, we choose that S, and then we put this S into A. Okay, and so that is the algorithm. Now let's, oops, take the analysis. Suppose that S1, S2 up to Sk are selected by the greedy algorithm in this order. So we first pick set S1 and then pick S2 and so on. Then we let this Ci be up to, from S1 up to Si. Then, okay, then this F of C sub I plus 1 minus F of sub Ci is greater than or equal to. So this has not, been covered. So anything that has not been covered over a optimal solution. So then what we want to know is that what is the upper bound of K? Okay, so we can show that this upper bound of K is less than or equal to optimal solution times 1 plus log of gamma. Gamma is the maximum size of this Si. Hence, of course, it could be at most n. So that means that we have these, this K, the upper bound of this K will just be so you can think of it as a optimization ratio. So that's log n plus 1 is the optimization ratio. All right. So what is the meaning of the submodularity? The meaning of it is the earlier the better. Okay, and then monotone increase in gain. Okay, so that's so much for greedy algorithms for now. When we have time, we'll revisit this issue later. But okay, so from now on, we are going to use DP, dynamic programming, and greedy algorithms as our basic algorithmic techniques. Okay, so when we look at graph algorithms, when we look at some other algorithms, we will always try to base our algorithm designs on dynamic programming and greedy. So when they are not enough, then we're going to look at new algorithm design techniques. But dynamic programming and greedy algorithms are the most common techniques in algorithm designs. Okay, so with this, so this slide concludes this video.